Welcome students. In this video lecture, we are going to learn about two-dimensional heat equation in infinite plates, especially with the short edge x equal to 0. When you consider two-dimensional heat flow, it will be along curves instead of along straight lines. Where we studied one-dimensional heat flow along straight lines, but two-dimensional heat flow will be along curves which lie in parallel planes, and we study along plates instead of there we would have studied in rods and bars, right? So here we used to study the heat flow over a square plate or a rectangular plate or even on infinite plates. So first let us see the equation governing two-dimensional heat flow. This equation, dou squared u by dou x squared plus dou squared u by dou y squared, which is equal to 0, which is written as del squared u equal to 0 or just uxx plus uyy equal to 0. This is also known as Laplace equation. This equation is the two-dimensional heat equation, where here u denotes temperature at a point x comma y. And these three are the various possible solutions of Laplace equation using the method of separation of variables. So these three are the various solutions. Among these, either solution 1 or solution 2 will be the correct solution depending on the boundary conditions of the specific problem. So let us see a problem here. So look at this problem. An infinitely long rectangular plate is bounded by two parallel long edges and one short edge right angle to them. The breadth of this edge x equal to 0 is pi. This edge is maintained at the temperature, a function of y is given, while all the other three edges are at 0 temperature. Evaluate the steady state temperature at any point of the plate. This is the problem. So let us now see. There is a infinite long rectangular plate, and you can see here this particular infinite plate is specified by this short edge x equal to 0, because when you have x equal to 0, it will be y-axis. So this is x equal to 0. So this line is the short edge. So the plate will look like this. So when you have short edge x equal to 0, it is this particular plate. And we need to fill the temperatures on all the four edges. So let us see. This edge is maintained at the temperature. Which edge? The edge x equal to 0. So where you have edge x equal to 0, this edge. So this is the edge x equal to 0, which is maintained at this k into pi y minus y squared, where all the other three edges are maintained at 0 temperature, 0 degrees Celsius. So now let us see how these four temperatures are defined. Now take this particular edge. Now in this edge, see, this is x-axis and this will be y-axis, is it not? So here along this line or along this edge, x is equal to 0, but y varies. So y is moving like this. So y will be variable on this edge. So y is y, but x will be 0. So x is 0. So u of 0 comma y equal to given by this temperature we have put. Now look at this particular edge. When you observe this edge, x is moving. X is moving, but y along this edge will be 0. So that's why you have u of x comma 0 equal to 0. Now come to this upper edge. Look at this upper edge. X is moving. See, x is variable. So x will be x only. But what will be y along this edge? Y along this edge will be this distance. What is this distance? Pi. So y will be pi here. So this is u of x comma pi, again, which is equal to 0. Now let us come to this broken edge. When you come to this broken edge, either x will go to infinity or y will go to infinity. First we should analyze that. So when you observe this broken edge, which is going to infinity here, x is going to infinity. So along the x direction, this long plate is going to infinity. So x is infinity and then y will be variable. So this is again 0. So only this is non-zero temperature, while all the other three edges are 0. So when you observe here, One will be given as non-zero temperature and the other three edges will be given as zero temperature. And let us move on to the correct solution. So how to start the problem? We need to first write the two-dimensional heat equation. Now, since the non-zero temperature, you should look at the non-zero temperature. Which variable is present here? According to that, we have to select the correct solution. So here, the variable y is present. So when variable y is present, this is the correct solution. You have to write cos and sine in terms of the variable which is present in the non-zero temperature. Since y is present here, correct solution will be C1 cos Py plus C2 cos Py into C3 e power Px plus C4 e power minus Px. This term is in terms of y, the other term will be in terms of x. So this will be the correct solution for this particular problem. Now let us write the boundary conditions. So the boundary conditions will be the 4 edge temperatures. So what are the 4 edge temperatures? 1, 2, 3, 4. So these 4 edge temperatures will be the boundary conditions. One by one we should write. So when you are writing one by one, always try to write these two zero conditions first. In the third position, write this condition having infinity. Last you should write the non-zero condition. So 1, 2, 3, 4. So in that order, if you write, it will be easier for us to solve. So boundary conditions we have written. So 4 boundary conditions you have. Now let us apply the boundary conditions one by one. So take the first one, apply 1, u of x comma 0, 0. So this is the correct solution, u of x comma y, first write that. And in that you have to put y 0, y 0. So when you put y 0 here, sin 0 will be 0, cos 0 will be 1. So what is the answer of the first term? C1. Into second term we are not touching. We are not touching x. So the condition says this is equal to 0. So when this will be 0? When C1 is 0. So the result is C1 equal to 0. Now let us move on to the second boundary condition. What is the second boundary condition? U of x comma pi 0. So take that. U of x comma pi 0. So which is pi? Y is becoming pi. X is x itself. But in the place of y, you have to substitute pi. So take the correct solution. In the place of y, let us substitute pi. See, already C1 we got 0. So this will become 0. And here, in the place of y, you have to substitute pi. So this becomes C2 sin p pi into the x term. X we are not touching. So this will come just like that. And the condition says this is equal to 0. This is equal to 0. You have to put that 0 here. And when you observe this, you should not touch the term having variable. I have already said the variable term we should not touch. So which needs to be 0? Either C2 will be 0 or sin p pi will be 0. So this term, either C2 0 or sin p pi 0. If you assume C2 0, since already C1 also 0, now when C2 also becomes 0, the entire term C1 and C2, when it is 0, the entire u will become 0. This is known as a trivial solution, which we do not need. So what has to be 0? Sin p pi has to be 0. Sin p pi has to be 0. And we know the famous formula sin n pi 0. So comparing these two, you have p pi equal to n pi or p equal to n. So the result here we get is p equal to n. Now let us move on to the next boundary condition, the third one, u of infinity comma y 0. So here, which is infinity? In the place of x, you have to put infinity. So take and write the correct solution. In the place of x, we shall substitute infinity. So y term is just y, we are not touching the y term, but since already C1 0, this term is becoming 0. So you only have C2 sin py into, in the place of x, when you put infinity here, e power infinity plus C4 e power minus infinity. And the condition says equal to, right side should be equal to 0. So this is equal to 0. You have to apply that. This is equal to 0. Now let us substitute. What is e power infinity and e power minus infinity? You should remember that is the basic values of exponential. So e power infinity is infinity. E power minus infinity is 0. You should remember. When you substitute here, e power minus infinity is 0. So this term will become 0. So here you will have C3 into e power infinity is infinity. And the condition says final answer has to be 0. So you should observe only when you have 0 into infinity, that will make 0. Only 0 into infinity will become 0. So from here you get C3 has to be 0. So this is the third result. Now let us go to the fourth boundary condition. But fourth boundary condition is a non-zero condition. Right side we have a term which is not 0. So before applying any non-zero boundary condition, usually we have to generalize the solution. So let us see how to generalize. What are the three answers we have got so far? First we got C1 0, next we got P equal to N, and the third we got C3 equal to 0. Now substitute these three answers in your correct solution. So this is the correct solution. Substitute these three answers. So C1 0, and in the place of P you have to put, so this is 0. C2, in the place of P you substitute N, sin NY. Coming to the second term, C3 0. So you only have C4 e power minus P. In the place of P you should substitute N, so minus NX. Now look at this. We will get like this. C2 into C4. All the constants together you have to cluster and you have to generally write Cn and you have to allow n from 1 to infinity. So when you do that, you get Cn. C2, C4 becomes Cn and you have to put a summation n equal to 1 to infinity. So this becomes most general solution. So this is the most general solution. Now in this most general solution, you should apply the last boundary condition. U of 0 comma y equal to k into this. So let us apply that. So this is u of x comma y. What is u of 0 comma y? What is u of 0 comma y? X has to become 0. So in the place of x, we have to put 0. So when you put x 0, where you have x here? E power term. So e power minus nx. So here you put x 0, e power 0 becomes 1. So this is the term you will get. U of 0 comma y will become sigma cn sin ny. And the condition says this is equal to, what is the right side? K into pi y minus y squared. But when you observe, this is just a function of y. So let us say f of y. So look at this. Is it not your half range sine series? So let us compare this with your half range sine series. So I have written the formula for half range sine series in the interval 0 comma pi. Because here the plate, the length of the plate you should observe, it is 0 to pi. So here only you have. So in 0 to pi, what is the half range sine series? That formula we have taken and written here. And this is the Bn formula. So look at this. Substitute, compare this and this. Is it not your half range sine series? Yes, in the place of Cn, here you have Bn. So the answer of Cn, the formula for Cn is the same formula of Bn. So substitute here. Instead of f of x, here you have in terms of y. So write the formula in terms of y. And in the place of f of y, now we should substitute k into pi y minus y squared into sin ny dy. So the same Bn formula we shall use for Cn, but instead of x, you have in terms of y here. So everything is coming in terms of y. Now look at this. How will you integrate this? Do you remember? You have to use Bernoulli's law. Yes. So this is our Bernoulli's law. Keep the first, integrate the second, minus differentiate the first, integrate the second. It goes like that. So look at this. Keep the first term, k into pi y minus y squared. K we have taken out, constant. Integrate the second. So sin when you integrate, minus cos ny by n. Minus differentiate the first. So pi y minus y squared when you differentiate, pi minus 2y. Integrate the second. Cos when you integrate, sin minus sin ny. By again n will come, so n squared. Plus, now this is the first term. Differentiate the first, minus 2. Integrate the second. Sin when you integrate, minus cos. So minus cos will come, plus cos ny. Again by n will come, so by n cube. And integration is over. We have to apply the limit from 0 to pi. So when you apply in the place of y, you have to put pi, upper limit, minus in the place of y, you have to put 0. So these are the values of cos 0, sin n pi, cos n pi, everything. So when you apply the limit, in the place of y put n, cos n pi, in the place of y when you put pi here, sin n pi becomes 0. So all that. So this is the final answer of Cn. So this is the final answer of Cn when you substitute and get the answer. So 1 minus cos n pi you will have. So substitute 1 minus 1 per n, which becomes 0 for all n even integers. And when n is even, this is the answer of Cn. So this answer of Cn you should substitute in the most general solution, and this is the required steady state temperature. So this is the final answer. So using the concept try to solve these two problems.